Yeah, this is a joint work with Vahid Asadi, Tom Gur, and Igor Shinker. Here we design new worst-case to average-case reductions for a few problems. So the plan of this talk is as follows. First, we will talk about worst-case to average-case reductions, why we want to design them, and how we do this in our work. Then we'll have an illustrative example of matrix multiplication. That's the problem on which we're gonna show all of our techniques. So we'll show how to do worst case to average case reductions for this problem using some tools from Additive Combinatorics. And finally, in the last couple of minutes, I'll discuss how these techniques seem to apply to other computational settings and to other computational problems. Please do ask questions during the talk. That would help. Okay, so let's start with worst case to average case reductions. There are many problems for which we do know worst case to average case reductions. Say in the early 90s, Lipton started studying program testing, and he showed that permanent has worst case to average case reduction. So for classical problems, worst case to average case reductions usually work via self-reducibility, a random self-reducibility. You just say, whatever input I have, it's essentially as hard as a random input. That's what essentially Lipton did for permanent. Later, Aitai showed this for certain lattice problems, and as we know now, this led to a very powerful and beautiful area of, say, lattice-based cryptography. Also for like standard number theoretic problems in cryptography, like discrete log, RSA, quadratic residue, they all are random self-reducible, so they all admit very efficient worst case to average case reductions. Also for a bunch of problems, so even classes of problems in high complexity classes like Sharpie, P-space, we also know worst case to average case reductions, efficient ones. All right, but nowadays we actually want to design super efficient worst case to average case reductions. We actually want to design them in the fine-grained complexity framework. Why? Because say you believe that three-sum problem takes time n square on in the worst case. If you could design worst case to average case reduction for this problem, very efficient one that doesn't take time n to the 10 but runs in, say, subquadratic time, then you have average case reduction for, say, three-sum, and then maybe from this fine-grained assumption you can construct, say, crypto primitives, right? That usually require some average case reduction. So in the past 5 years, we had a bunch of beautiful. We as a community had a bunch of beautiful results in this area. We proved average case hardness for several fine-grained problems like orthogonal vectors, three-sum, k-clique, some algebraic problems, and we try to build cryptography based on these assumptions. But I think even though there are many beautiful results, I think it's still fair to say that we don't know how to build, say, public key cryptography based on well-established, really well-tested fine-grained assumptions yet. So there is work to do. We want to understand efficient worst case to average case reductions. Any questions so far? Good. All right. Yeah, of course, there are many more problems that admit worst case to average case reductions, but I just wanted to give you a flavor of some of them. So this result is we design what we think might be a new technique for worst case to average case reductions. And we show how to apply it to algorithms for matrix multiplication, to static data structures for all linear problems. So let me just give you an example. So that means you have some linear problem you want to solve. That is, linear means it's given by a matrix, and then the problem itself is given a vector x, output matrix times this vector x. So for any such problem, if you have a data structure that solves it on a fraction of inputs, even on sub-constant fraction of inputs, I'll give you equally efficient data structure that works for all inputs. Equally, I really mean like its running time will be 4 times the running time of the original one. Its space requirement will be 4 times the space requirement of the original one. We can make this 4 or 3 if you really care, but yeah, it's really same running time, and it works for all inputs. Same in the streaming or online setting. There is this problem online matrix vector multiplication. Here I give you a matrix, say n by n matrix, take reasonable time to preprocess it, and now I'm sending you vectors one by one. Output me the product of this preprocessed matrix with the vector. So you can trivially answer each query in some n squared time by multiplying a matrix with a vector. So for example, you can answer n queries in n cubed time. But if I send you the n vectors together as a batch, you would do matrix-matrix multiplication, and you would have solved it much faster than in cubic time. And this problem, we're just trying to figure out if this sequential setting, online setting, if it's inherently harder than the batch setting or not. And here we also say that if you can solve this problem for a fraction of inputs, maybe you can only solve it for some structured matrices efficiently. Then we'll take it from there. We'll get a equally efficient algorithm that works for all matrices and vectors. Okay? We'll also show how to apply these techniques to essentially in the error correcting code setting. For different polynomial evaluation problems. All right, so we'll discuss some applications of these techniques in the end of the talk. And now let's see the techniques themselves in the case of the matrix multiplication problem. Any questions? So from now on, we're going to be, oh yeah, I forgot, there are always two ways to view worst case to average case reductions, right? So one way would be to design new worst case algorithms. Say you can multiply matrices efficiently, like in quadratic time, but only for some structured classes of matrices that have structure. So if the fraction of these matrices is reasonable, then we can take it from there and give you a new algorithm that has same running time, but works for all matrices. Or another way to view worst case to average case reduction is that, okay, if you have a worst case lower bound, we can extend it to average case lower bound, and this also might be useful, right? It might be useful for cryptography or other similar applications. All right. Let's talk about matrix multiplication. This is a classical problem. Given two matrices, we want to multiply them. The computational model here is a standard normal algorithms, right? I mean, it might be hard to imagine for this audience, but let's pretend we have like a computer and we want to and we want to multiply matrices efficiently. Okay. So the best algorithm for this problem is currently due to Josh Allman and Virginia Vasilevska-Williams. It runs in time n to the 2.37286, I believe. And here the problem we want to solve is the following. Assume you have an algorithm that works only for a fraction of matrices. Can we boost it into an algorithm that works for all inputs? And here, all our techniques work even when alpha is subconstant. Like it might be 1 over 2 to the, say, square root of log n, for example. Okay, so we're going to be working with even subconstant fraction of the inputs, and we'll boost it to all matrices A and B. Okay, so that's our main result for matrix multiplication. If you have an algorithm that solves matrix multiplication on alpha fraction of inputs, then we have a new algorithm, alg prime, that runs in time t times not too terrible function of the of alpha that works for every A and B with probability 99%. Or this probability is easy to amplify. You can make it all but something negligible in it. Okay. So let's see how we could do this. We'll start with a we'll see how to do it, but let's make a few assumptions. So for the purpose of the presentation only, we will assume that our field is F2, and this is actually not a simplifying assumption. That's the hardest case, because for matrix multiplication, it turns out like you can view matrix multiplication as degree 2 polynomial in the entries of two matrices. Degree 2 polynomial you can interpolate by querying it at like 3 points or so. So if your field is large enough, you can actually use some other simple tricks to achieve this result. So actually for this specific problem, F2 is kind of the hardest case. We will assume that the original algorithm, average case algorithm, is deterministic, but by standard techniques, it's without loss of generality. And we'll make this simplifying assumption. This is the following assumption. Look, I know that the number of pairs, the fraction of pairs which are good, where our algorithm works, is alpha. And we'll be designing an algorithm that works for all A and B. So given A and B, I will tell you how to multiply this A and B. I'll just assume that the A that I received is kind of average A. That is, the fraction of B's that are good for this A is at least alpha. For some A's, the fraction of B's of good B's is 0. For some, it's 2 alpha. I'll just assume that the A I received is alpha. So I'll kind of only correct error in this talk for matrix B In the paper, obviously, we then repeat the same procedure to correct problems with the matrix A. So today we'll generate 1 million of random matrices to correct all problems with matrix B. In the paper, we generate 2 million of random matrices, do the same with A. That might be a feature of it.
And by the way, there's a question in the chat.
Ryan has a question in the chat. I'll read it. So I couldn't quite hear. Did Sasha say that fast matrix multiplication over F2 implies fast matrix multiplication over any field? That is open as far as I know. But
No, I never said this. Okay. All right. Yeah, so we're going to do worst case to average case reduction for matrix multiplication over the F2 field. Yeah. Now, this is the assumptions we make. The main one is that given matrices A and B, worst case matrices A and B, we'll assume that the number of good matrices B for this matrix A is at least like alpha fraction. Okay, so there is a folklore way to reduce worst case to average case matrix multiplication when your average case algorithm is very good, when it works on more than 3/4 of matrices. This is just BLR type reduction. I think this is a folklore, but it was certainly known to the BLR authors in 1990. So here's how we can do this. I want to multiply matrices A and B. I have an algorithm that works with for more than 3/4 of the matrices. I'll just sample 2 random uniform matrices, R and S. I'll write A as a sum of R and A minus R. I'll write B as a sum of S and B minus S. Note that while these matrices are correlated, each of the 4 matrices is actually uniformly random. And also say R and S or R and B minus S are independent. Okay, so now I can actually use my algorithm to multiply R and S, just to compute these 4 cross products. This is computed like not correctly with probability 24%, 24% here, 24% here, 24% here. So I still have 4% that all of these products are computed correctly. Then these 2 give me R times B, these 2 give me A minus R times B. So I get A times B with probability 4%, but for every A and every B. I start with an algorithm that works only for some matrices. I get an algorithm that for every A and B has some non-negligible probability of success. Now I just need to amplify this probability of success for every A and B, but that's easy to do. I have an algorithm that for every A and B achieves, this alk prime, sorry, computes their product correctly with probability 4%. Now I'll just boost the probability. For this, I will use Freewell's algorithm. That's the classical algorithm that says that, yeah, maybe matrix multiplication is a hard problem, but matrix multiplication verification is actually easy. You can do it with randomness in quadratic time. So I'll just multiply these 2 matrices, use Freewell's algorithm to check if my answer is correct. If not, then I'll do it again, again, and again. I don't need to do it too many times because I already have a reasonable probability of success. So from this, I can get an algorithm that multiplies any pair of matrices with probability 99%. All right, any questions? So this build, yeah?
What is your ultimate goal here? You want to get this thing with probability 1 at the bottom? Or
Here, no, I mean, I can amplify it to 1 minus 1 over n. No, this probability doesn't matter. My ultimate goal is start with a very weak algorithm. This algorithm already works on 3/4 of all matrices. That's a lot. And actually, for this type of reduction, 3/4 is tight. You cannot use this reduction to say that weaker average case algorithm will give you a worst case algorithm. My goal is to start with very weak average case algorithm where this is not 76%, but sub-constant. Actually, like exponential in polylog. Yeah.
So what do you mean by this type of reduction?
I mean this reduction. Yeah, I mean BLR reduction. Yeah. Sorry, someone. Yeah, Roy. Yeah. Okay, so let me show you one example. So this reduction fails when there are when the algorithm works with probability less than 76%, and let me show you an example. This is not tight example, but that's all right. So assume I have an average case algorithm that works correctly if the first entry of B is 0, and just gives me no information whatsoever if the first entry of B is 1, right? Now, whatever I sample, when I want to write B as a sum of two matrices, one of them must have 1 in this coordinate. So when I will multiply this B minus S with anything, I'll just get no information. Okay? So I cannot just apply the same BLR reduction here. Specifically, like in this case, if my average case algorithm is like this. Make sense? The algorithm will definitely fail on one of the two matrices that I used to write B as a sum of two matrices. So what can we do in this specific case? Assume my average case algorithm is exactly this. How do I design a worst case algorithm? I can just pretend, so if the first entry of B is 0, the average case algorithm works correctly, so I only need to handle the case when the first bit of B is 1. So I'll pretend it's 0, use my algorithm, and then just fix the error. I'll just locally correct the error. If I multiply this matrix instead of B with the first bit flipped, I can easily correct the answer, because the answer would be the product of A and this modified B plus one column of A. But I can easily correct that. Like, this takes linear time. Linear time doesn't matter here. It's like super quadratic. Is there a question? Can you read?
That is the question from before.
Okay. So, and this is a high-level idea of how we're going to do worst case to average case reduction for matrix multiplication in general. So we'll try to find some structure in the set of good matrices where our average case algorithm works, and then we'll try to make some local changes in B prime to put in B to put it in the class of good matrices, and then correct these changes like we did here. Here we added a column of A to correct the changes. We'll try to do something like that, like this in general. Okay? Any questions so far? So it turns out that hoping that you can always flip a few bits in B and get in the class of good matrices, that's too ambitious. That's not necessarily holds always, but we can do something similar. So for this, we'll use some tools from Additive Combinatorics. Let me introduce one or two definitions. So say I had a set of good vectors, good matrices, in some vector space, then its sum set 4 times G is just a set of all sums of 4 tuples from the set. Okay? And there is this classical result in Additive Combinatorics. It's called Bogolyubov's lemma. It just says that if you have a huge set, a set of large density, then its sum set, its 4G, actually contains a huge subspace, highly structured set, subspace. Okay? So that's what we're going to use for our worst case to average case reductions. And here's an example how we could use it. Questions? Maybe? Okay, so I want to multiply A and B. Let me define the set of good matrices B. Those are the matrices where average case algorithms works correctly. And we already assumed its fraction is reasonable. It's at least the alpha fraction of all matrices B. Okay, so by Bogolyubov's lemma, 4 times G contains a huge subspace. Okay? So for every matrix from this subspace, because it's in 4 times G, I can write it as sum of 4 matrices. Each is a good matrix. What does good mean? Means the average case algorithm works correctly for this matrix. So I can write B as a sum of 4 matrices, and for each of these 4 matrices, I can compute the product correctly. So whenever I want to multiply A by B, I can just compute this S1, S2, S3, S4, and multiply A by S1, S2, S3, S4. I know for sure the average case algorithm works for them correctly. So it will give me the correct product. Okay, that's just the first step. There are a couple of issues. If you see issues, yeah, raise, yeah. Yeah, there are lots of them. For example, one would be B can be written as a sum of 4 things. How do I actually do this efficiently in some like quadratic time or even faster? Another one is, okay, I can handle matrices from subspace V, but what have I gained? The subspace V is actually smaller than the original set where I could compute product correctly. So far I only lost a little bit. But yeah, we're going to use the fact, obviously, that V has a lot of structure. So we want to say, since I already can compute product for a set of matrices that have nice structure, I will use it to compute products for all matrices B. Okay, so two main issues are that first, how do I write B as a sum of 4 matrices from G, even though I know there is such decomposition? Second issue is, what do I do with B's which do not belong to this nice subspace V? All right, so for the first issue, we'll use a different version of Bogoliubov lemma. So let me remind you. So yeah, we're going to handle the first issue now. Bogoliubov lemma says a huge set implies some set has a large subspace. Now there is a probabilistic version of Bogoliubov lemma. It says a cooler thing. So if you have a huge set, not only does it have a large subspace, every element in this subspace has very many representations. That is, if you want to write B as a sum of 4 things from G, you can just sample 3 of them at random. The fourth one is fixed, right? You want B to be sum of them. The fourth one will be in the set of good matrices, like all of them will be set in the set of good matrices with high probability. Like if you just sample S1, S2, S3 at random, the probability that they're in the good set is already alpha cubed by the density of the good set. So for putting this in the good set, you're paying just a factor alpha square instead of alpha. It's essentially for free. So this is a probabilistic version of Bogoliubov lemma. In order to write B as a sum of 4 good matrices, you can just sample 3 at random. The fourth one is fixed. And you hope that they all are good. With reasonable probabilities, this will actually happen. So in order to resolve the first issue of representation of B as a sum of 4 good matrices, we'll use probabilistic versions of Bogoliubov lemma. We'll just sample matrices at random, and this will work with good probability. But actually, we're going to be greedy here. These versions of Bogoliubov lemma, they only give us not so good codimension of subspace V. This will work for average case algorithms that are good for constant fraction of matrices, but we want to handle sub-constant. So we'll use stronger versions of Bogoliubov lemma. In 2012, Sanders proved a quasi-polynomial version of Bogoliubov lemma. Same thing, but codimension, instead of poly in 1 over alpha, is polylog in 1 over alpha. That's much better for us. We can now handle much weaker average case algorithms. Except, again, we need probabilistic version of this lemma to write a vector, to write a matrix as a sum of 4 good matrices. So that's something we prove in this work. We generalize, we take quasi-polynomial Bogoliubov lemma, we take probabilistic Bogoliubov lemma, we merge them, and we get probabilistic quasi-polynomial Bogoliubov-Ruja lemma over all fields, over all finite fields. Okay, so that's how we handle the first issue. We can efficiently write every B in V as a sum of 4 good matrices just by a probabilistic version of Bogoliubov lemma. Okay? Yeah?
There's a quick question. So, also, Ryan asks, also it's unclear that size of G, the good set, should be that large for every A. How does that
Yeah, so sorry, that's the part that you didn't hear because I was there. So we only for this presentation, we assume that A that we are given has this property that is kind of average A, that is alpha fraction of B's is good for it. And we correct all the problems we may encounter with B. In the actual paper, we repeat this procedure for matrix A after this. Okay. All right, so we had another issue. How do we handle matrices B which do not belong to subspace? Here we're going to heavily use the fact that V is a structured set. It's a subspace. Okay, so one way to handle matrices that do not belong to space V is like very simple low-rank random matrix shift. So we already have an algorithm that computes AB for every B from a large subspace. say it's a subspace of codimension k, where like k is some fraction of alpha, just ignore it. Think of it as a constant, right? Some like a codimension is like 10 maybe. Now we want to compute AB for matrices that do not belong to this subspace. Here we don't even care what this subspace looks like. We'll just say that for every subspace there is a way to generalize matrix multiplication from subspace to all matrices. We just sample a random matrix of rank 2k, where k is a codimension of V. And then it's very easy to see that actually for every matrix B, when you add a random matrix of low rank, of rank 2k, you hit a subspace of codimension k with reasonable probability. It's probability 1 over 2 to the k essentially. So now when I'm given a matrix B which is not in subspace V, I just add a random, I generate a random low rank matrix, add it. Now for this matrix, I can use my algorithm for the subspace V, and I need to correct this error that I introduced, this low rank matrix. But I actually generated random matrix, a random low rank matrix together with low rank decomposition. It's like a product of two small matrices, n by 2k, 2k by n. And for these matrices, it's very easy to do matrix multiplication manually. Multiplication, because like they are small, you can really efficiently multiply matrices by small matrices. So I'll just correct this, this error actually manually. I'll just compute A times RB in some quadratic time. And now, yeah, AB is just sum of these two things. One I can compute thanks to the previous algorithm, the other one I just compute because it's low rank. Okay? Any questions so far? Yeah.
This is kind of like the generalization of the bit flip thing.
Yeah. Apparently bit flips don't work in general, it's not enough, but low rank shifts apparently are sufficient. Yeah. There is another way we can actually do this. Like low rank random matrix shift is not the only way you can do it. Yeah. You can embed it into larger matrices and then you'll hit any subspace of low codimension. Yeah. All right, so we had two issues. We resolved them both. For the first one, we used probabilistic versions of Bogolyubov's lemma. For the other one, we used low-rank random matrix shift. Okay, let me mention in the last couple of minutes, a few more applications. So this technique seems to apply in a bunch of other computational settings too, even when you don't have a computer. So for example, for matrix multiplication, yeah, it says the following. If algorithm runs in, say, time n to the omega and computes matrix products correctly on this fraction of inputs, like definitely subconstant, then I can give you an algorithm that runs in essentially same time and works for all A and B. That's what we get for matrix multiplication. Now for static data structures, if you have a static data structure for some linear problem, any linear problem, this reduction works for all linear problems. That is given x, you compute m times x, and you succeed only on polynomially small fraction of inputs. Similar ideas give you data structures that solves your problem, any linear problem, for all inputs with essentially the same space and essentially the same time. You just multiply them by 4. Here we need to add a couple more technical details. So previously for matrix multiplication we have efficient verification procedure, Frival's algorithm. We don't have efficient verification for all linear problems. But turns out in the setting of static data structures you can use the power of preprocessing plus some epsilon bias sets to imitate efficient verification too. And finally, like you can do random low-rank matrix shifts because there are no matrices anymore. You're working with vectors. Turns out that in general, for vectors, instead of low-rank matrices, you can use sparse vectors, and they play the same role because multiplying matrix by sparse vector is something that you can do efficiently. You can correct these errors locally and efficiently too.
What about the blow-up due to alpha? I mean, there's some blow-up in the production depending on alpha. Right?
So here I just fixed, for the presentation, I fixed alpha to be 1 over poly n. And then you get these parameters. I think for static data structures, it's going to be, so in the paper it's written as log to the 5 of 1 over alpha. We can do it now log squared of 1 over alpha, very strong version of polynomial Freeman-Rouget conjecture would even imply log of 1 over alpha. Okay, now for the setting of streaming or online algorithm, we can do this for online matrix vector multiplication problem. Yeah, important thing, like usually or often online matrix vector multiplication is defined over the Boolean semi-ring. There we don't know how to apply our techniques. We work over finite fields. It's also a well-defined and well-studied problem. So here, if you have an algorithm that works on essentially like almost polynomial fraction of inputs, then we can give you another algorithm that solves OMV with the same running times and same space, if you care, on all inputs.
What is the time here, Sasha, per update? Or
Yeah, for a query. Yeah, query time. Yeah. Yeah.
So if you replace the 1 over n to the little of 1 by p, or alpha, whatever,
Yeah.
then does the time get multiplied by something that depends on?
So this dependence on alpha is different for different computational settings. Here, let me think. T is
Like p to the log 1 over p is 1 over p to the log 1.
Yeah, here it might be, in this setting it might be just polynomial in alpha, yeah. Yeah, probably 1 over alpha to the 5. Yeah, this requires, actually here, recall this good space V. So it exists, but for certain applications, for example, for online matrix vector multiplication, we need to learn this space V, which has small codimension and succinctly represent it. So we can represent it by basis for its orthogonal complement. And we need to find it efficiently. But the good thing is that apparently for all this Bogoliubov's lemma, orthogonal complement of V is just, its basis can be taken just the set of vectors of the indicator function of your good set with the largest Fourier norm. So we only need to learn the largest Fourier coefficients, the largest squares of Fourier coefficients of essentially explicitly given function. And for this, we have very efficient algorithms, Goldrick-Levin and its generalization to other fields. So we apply these tools here. Finally, there are some applications of these reductions to, say, error correction codes. For example, for certain codes like read-Muller, you can do the following thing. Alice sends a message to Bob. If there are very few errors, Bob can efficiently locally decode the message. If there are slightly more errors, Bob can locally least decode it. So these reductions, when you apply it to codes like read-Muller, says the following. If Alice can send to Bob a few more bits which are not flipped, which Bob receives exactly in the way Alice sent them, just a few of them, then Bob can efficiently locally decode in the least decoding regime. He can uniquely decode in the least decoding regime. That's kind of worst case to average case reduction for ECCs that is implied by these techniques. Okay, that's it, and thank you for your attention.
Thanks. Let's keep